have spent almost a year of my life in San Diego in 2-week chunks. And every time I go to San Diego, first thing I do is I head to the zoo. And the first thing I do when I get to the zoo is I go look at the orangutans. And I say to myself, wow, if those guys had just pitched back a few degrees, they'd be here instead of me. And I'd be in the San Diego Zoo being watched by things with orange hair. They're really smart. And after spending a lot of time at the zoo, I've seen a full range of behaviors. But it took me almost 20 years before I took that picture of an orangutan using a tool. Pretty smart. But on the other hand, not smart enough. Not smart enough to compete with us. And wonder why that is. And that's the subject of what I'm talking about today. Why is it that we're here instead of the orangutans? To tell the story, I'm going to start with right now and go back about 50,000 years. I'll conclude that it's because we can tell stories and they can't, at least not to the same degree. I'll talk about what follows from that in terms of what kind of research you have to do. I'll tell you about the state-of-the-art in story understanding systems, and I'll show you that on top of a very simple substrate, you can build quite a lot of stuff. And then I will conclude by talking about why none of this matters unless it's connected to vision ultimately. So that's the agenda for the next 45 minutes or so. And of course, you can't give a talk on AI these days without the obligatory Watson, Siri, Igloo, and self-landing airplane slide, which I borrowed from Tommaso some time ago and rearranged a little bit. So maybe 500 years from now, when people are talking about artificial intelligence, they will have said, oh, it began with these things, but I rather think not. I rather think the anchor will probably be about 55 years ago when Marvin Minsky published a paper titled Steps Toward Artificial Intelligence. It told us what to do. Unfortunately, what it told us to do wasn't quite the right thing, but it did launch a great deal of activity, including the same year, a program that could do symbolic integration the same way an MIT freshman does symbolic integration. And boy, did it seem like we were on the way to really rapid progress. When you can make a program do that, surely the rest will be easy. Turned out the rest wasn't easy, and here we are 55 years later, still without a very adequate theory of what goes on inside our skulls when we think. But maybe that won't even be the anchor, even though it did launch decades of work that led to the sorts of things I put on the slide. All these sorts of things have a lot to do with application. Any artificial intelligence course in the world is a selection from this menu. But still, it may not have been that paper by Marvin Minsky may not be considered the beginning. This will probably be considered the beginning. If not, it's the original paper by Turing on computing machinery and intelligence. It's the paper that's known for the introduction of the Turing test. I think Turing didn't give a damn about the Turing test. Turing's paper actually contains about 3 pages on the Turing test. It contains about 10 pages on telling you what a computer is. After all, this was a day when computers weren't much there. It contains additional material on why it is possible to make an intelligent computer, and it concludes with a program of research. So it looks to me like, in reading, I've read this paper 10 times because I assign it to my class, so each year I reread it. And every time I read it, I became more and more convinced that Turing actually didn't care about the test. He was just using that to get the question of what is intelligence out of the way. Because he really wanted to talk about why computers could be intelligent, and he didn't want to argue with, this is a philosophy journal, he didn't want to argue about what intelligence is. I think if Turing had taken Marvin Minsky's recent classes, he would have probably approached it a different way, because Minsky has introduced the notion of the suitcase word. The suitcase word, it's a word you can stuff anything into. And he notes that words like intelligence, creativity, emotion, these are not really things, they're collections of things. So if you say to me now, in light of what Marvin had said about these words, you say, is Watson smart? Is it intelligent? Then the easy answer is not to argue it, but to say, sure, it's intelligent. It's intelligent in some ways. Maybe not all the ways that a human is. Maybe superior in some ways. But since intelligence is a word that covers so much ground, it doesn't really pay to argue about whether something's intelligent. It might be better to argue about things on a finer scale. Does it have a model of itself? Can it talk about how it works? Can it have a model of somebody else? These are kinds of questions that derive from this notion of suitcase word. Well, that's 1950, and at that time there were a lot of popular arguments against the possibility of computers being intelligent. Number 5, there are disabilities. People would say, well, you can't make a computer that's intelligent because they can't do something. Enjoy strawberries and cream, compose a symphony like Mozart. But of course, that last one, compose a symphony like Mozart, that's a little dangerous to argue from that perspective, because that means everybody except Mozart has never been intelligent. And even Mozart wasn't intelligent because he couldn't compose plays like Shakespeare. So that's one of the kinds of arguments that was popular then. The Lady Lovelace one, well, that comes from 1840 when Babbage was building its computer. And even then, Lovelace was said to say, computers can only do what they're programmed to do, thus soothing the public. It would have been better if she said they can only do what they've been programmed to do and what we tell them how to, and what they discover how to do on their own. But that might not have had quite the same soothing effects. So this is when people started thinking about whether computers can think. And if we go back a little more, maybe 2,400 years, we get to the point where people started thinking about thinking. And I'll have to rely on the Greek students to tell me if this is approximately true or not. But Plato's most famous work was the Republic, except that's a mistranslation of the Greek word politia. And the Greek word politia is untranslatable, but it means something like society or something like that. And the Republic is actually about what goes on in here. It's a metaphor. It's a metaphor to what goes on in a state. It's a metaphor about what goes on inside your head. So 2,400 years later, Marvin Minsky published a book called Society of Mind, in which he talks about stuff going on in here. It's like the whole society of independent things. So it's really the same title that Plato used 2,400 years ago, and thinking about the same kinds of things. But I don't like to just go back this far. I like to go back 50,000 years, because that's when we started thinking. And it's interesting that we had our modern anatomical form for about 200,000 years, but we only started thinking about 60 or 50 or 60,000 years ago. For most of our existence, we were not much different from Neanderthals in what we could do. We made the same crappy stone tools for 10,000 years at a time without improvement. We just didn't seem to amount to much. We didn't build anything that lasted. We didn't paint caves like the ones we eventually started painting at Lascaux. So what happened rather suddenly, about 50,000 years ago, according to paleoanthropologists. It was more a discovery of how to use stuff that had already evolved than something that had evolved. Something that came along all of a sudden. The question is, what was it? Well, no one quite knows. The paleoanthropologist Ian Tattersall, who has written a great deal about the suddenness of this acquisition, says we became symbolic. Well, what's that? I mean, yeah, okay. So I guess those paintings at Lascaux and figurine and Bassan-Puy, they're symbolic, all right. But what exactly does that really mean? Well, Noam Chomsky, who's an admirer of Tattersall, says that what it meant is that we could take two concepts and put them together to make a third concept, and we could do that without limit. And everything there is important, especially the without limit part, because maybe those orangutans can do it a little bit, but we can do it a lot. We can put concepts together to make new concepts. So now fast forward a little bit, 50,000 years, and talk about what I find to be the most interesting set of experiments in cognitive psychology ever. This is the work of Liz Spelk, part of the center, except for the rat part. She doesn't do rats, she does people, but the rat part is important as a prerequisite, as a preamble to describing what Spelk is. Here's what you do. You take a rat, you stick him in a rectangular room, and each of the corner there's a little basket or cloth covering. And while the rat is watching you, you put some food in one corner underneath the cloth. And then you see what happens after you spin the rat around to disorient. And the rat, after being spun around disoriented, goes with equal probability to the diagonally opposite corners, as it should. You know, you can't know about these experiments without thinking we're just rats with big brains, because they're really smart. They got the geometry right. And you can repeat this with a small child or with a human adult, get the same answer. Are you with me? Now you paint one wall blue, and you repeat the experiment with a rat. What do you suppose it does? It ignores the blue wall and goes to the diagonal corners with equal probability. So does a small child. It's only a genius like me gets it right. Can somehow combine the geometry of the room with a blue wall. But you know what? The last part of the experiment is the part that amazes and fascinates me, and that is this. You can engage the human subject in shadowing behavior. So you read something to the human, and the human says it back to you as you read it, as if we were doing simultaneous translation into another language, except it's English to English. It's called verbal shadowing. And you start this process off before the person walks into the room. So they're continuously doing this verbal shadowing for the whole experiment. And what do you suppose happens? They go to the diagonally opposite corners with equal probability, even though they've seen the blue wall. And will report that they saw the blue wall. They just couldn't use that in figuring out what to do. Oh, I've got food here. That's because at MIT you can use food for adults too. So this has a couple of messages for us. One of the things that we humans can do is we can put stuff together. That's what being symbolic means. You can build symbolic descriptions. By the way, there are a couple of practical observations here too. Number one is we only have one language processor, and you can jam it. And you can jam it by overloading it with language. And so if you're reading your email right now, what that means is you won't remember a thing about what I said by dinner time. And the other thing it means is that the more words you have on the slide, the less people will understand you, because you're jamming a language processor, and they'll be reading the slide, listening to what you say. We actually did some experiments on this at MIT. We had a student do a tutorial on a programming language to a bunch of volunteers, that is to say, freshmen in his fraternity. And what he discovered is at the end of the experiment, half the material was delivered on the slide, the other half was spoken. And what he discovered was that they didn't get any of the stuff that was spoken. They only got the stuff that was written on the slide. And in fact, one of them said, "I wish you hadn't talked so much. It was distracting." So it's an example of how you can overload the language processor. So what I think is that this symbolic stuff makes it possible for us to build descriptions, and then you can string them into sequences, and then you get this. See, I know better than to talk while you're reading that. Yeah, and if you believe that, then the question is, what do you do about it? And what I think you need to do about it is derive from the methodological principles that were introduced by David Marr, Maso Paggio, a long time ago. And you have to, first of all, understand what it is you're trying to understand. And story understanding is what we're trying to understand, and it's extraordinarily pervasive. You recognize it as present in all of these contexts. And in fact, you might be surprised to see that last entry there, engineering. But if you listen to my colleague Jerry Sussman, who's a rabid electrical engineer, talk about this circuit, he's telling a story. He talks about how the signal comes in from the left and it walks right through the capacitor, which is invisible to it, and it presents itself at the emitter of the transistor, at the base of the transistor, and now there's a 3 tenths of a volt drop between the base of the emitter and so on, and it's just like telling a story going from right to left. So even engineering, it's a question of story understanding. Well, if you believe all that, and you believe all those places where story understanding occurs, then you have to say, well, here are the steps we're going to take to deal with it. We're going to characterize some behavior to finer grain. We're going to figure out what the computational problems are, and so on. you know, do all those kinds of things. And here's the character, here's the behavior we're trying to understand. This is a particular example of a story that had drilled into me by my father, who liked Shakespeare when I was a kid. So eventually it got imprinted. And what we're trying to do now with our story understanding is not understand real Shakespeare, but understand this summary of a Shakespearean plot. It's about 100 sentences in all, simple sentences. They're understood incidentally by Boris's START system, which does a syntactic analysis and produces for us a semantic network. But that's the competence we're trying to understand, is how we can take this story and understand more than what's in the story itself. For example, I could ask you, is Duncan dead at the end? And you would say, sure, somebody murdered him, but it's not explicit in the story. I could ask you a harder question. Why did Macduff kill Macbeth? And you probably would have to kind of trace back through here, and it'd take you a few minutes to figure that out. And then I could say something even more sophisticated, like, is there a Pyrrhic victory in this situation? And you might not even know what a Pyrrhic victory is until I remind you that it's something that first seems successful and then turns bad in the end. So that's the kind of behavior we're trying to understand, how it's possible to read a story like this and get all that kind of stuff out of it. So what are the computational solutions to some of those problems? Well, we astonished ourselves by discovering that we can illustrate a lot of human story understanding capabilities with a very simple computational substrate once we have the semantic network the system produces. First of all, we can make inferences using inference rules of various kinds. We have 7 kinds of inference rules now in our system, all of them driven into our system by the need to understand various sorts of stories. So some of them are extremely simple, like if I harm you, I harm your friends, and others are less certain. If you make me angry, I may want to kill you, and fortunately that's not always true. But if I'm searching for an explanation, that's the only one I can find, then I might believe it. So at the very bottom, we have a variety of rule types that tend to put cause-like connections between the events in the story. Then in addition to those rules, those common sense rules that operate very locally, we have concept patterns that operate very globally. So here's a concept pattern for revenge. I harm you, and eventually you harm me. That's some continuous path of connections. So this is really the system thinking about its own thinking. It uses the lowest level to create causal connections. That makes a graph. And then it thinks about its own thinking by inspecting that graph and reaching conclusions about concepts that it can find in that graph. Here's an example. This is the so-called Genesis system that we built, analyzing the story that you just saw in English. Everything that goes into the system is in English. The stories, the rules, the concept patterns are all in English. And of course you can't read that, but what you can do is you can see all this stuff in white, this stuff that's explicit in the story. All the stuff in yellow has been inferred by some kind of common sense rule. A few other colors there denote special cases, but that's the general trend. The stuff in white is explicit, the stuff in yellow is deduced. So if you zoom in on that, you can see some stuff. You can see that Macbeth murders Duncan, and that's connected to Duncan becomes dead. So that's how you know that Duncan's dead, and because he's been murdered, you have that inference rule. That's terribly simple. Here's a slightly more complicated one. This says Macbeth is Duncan's friend, and the reason is because they have a common enemy. So it's a kind of, the enemy of my enemy is my friend type of reason for concluding that. So those are rules at work, but also there are these long-distance patterns, these concept patterns that are at work too. And here I've clicked on Pyrrhic victory down here, and suddenly all this green stuff is lit up. Those are the elements in the story that contribute to this being a Pyrrhic victory. So let me zoom in on that as well. So what happens here is that on the very left, Macbeth wants to be king. And then shortly thereafter, he becomes happy because he murdered Duncan and became king, all that sort of thing. But eventually, through a continuous chain of connections, Macbeth harms Macbeth. so it doesn't turn out so hot. Yeah. So there's a Pyrrhic victory there, and that's determined by a surge that finds that long-distance connection. Doesn't matter how long it is. It's not a local phenomenon. It finds that long-distance connection. So with that simple substrate, you can do a lot. Here's the system working on two versions. He's working on Macbeth again. By the way, it works on all kinds of stories. Political conflict, law, medicine, doesn't matter. Here it's working on Macbeth again, though, but now it's using a model of an Eastern reader and separately a model of a Western reader. And we think differently. You know? This happens to be well, here's the difference. These were differences that were ferreted out by Morris and Peng back in the 90s. They did experiments with high school kids in a suburb of Beijing and in Wisconsin. And what they found was that there was a statistically significant tendency of the Asian students to see violence as a consequence of the situation that you're embedded in. Whereas the kids in Wisconsin see it as a consequence of you and with something wrong with you inside. So that's what we modeled this particular experiment. So on the top is the Asian view. Macbeth kills Macbeth right here because he's embedded in this revenge situation. Couldn't help himself. But in the Western view, Macbeth kills Macbeth because he's crazy. He's insane. So it's, to use the fancy terms, it's situational versus dispositional. Booking and answer questions, of course, that's easy enough. In this case, I'm switching now to a political domain. What happened in this particular case was that Estonia removed a Russian war memorial from the center of Tallinn. And the question is, what happened? And if you happen to be a friend of the Russians, you see it as a teaching the Estonians a lesson when they brought down their national web. And if you're a friend of Estonia, what you see it as misguided retaliation. So here's a sequence. I went over that pretty quickly. The Estonians remove a Russian war memorial. The next day, the Estonian national web goes down. Websites are based, all kinds of things happen. Everybody knows the Russians did it. And the question is, why did they do it? And it depends on who you're on the side of. One side you see it as misguided retaliation. On the other side you see it as teaching a lesson. What else can you do? You can even have some of the analysis driven by the questions you ask the system. This is again from Morris and Peng. This is a story adapted from a Morris and Peng experiment on these high school kids. The story's about a graduate student who murders his professor. So don't get any ideas about it. It's a grisly story. But the question is, why did he do it? And at first the system has no idea why he did it. But then you ask the system a question. Did Luke kill Shen because America is individualistic? And at this point, the Asian reader of the story inspects its own beliefs, decides that yes, it does believe that America is individualistic, inserts that fact into the story, and that unleashes a chain of reasoning that allows it to conclude, yep, on reflection, I do believe that. And he did know because it was individualistic. Whereas the Western reader has no such thing as memory, and its memory, its belief system, so it can't reach that kind of conclusion. Well, here's one that I especially like because it's inspired by Shimo's work. Once you have this idea that stories have concepts, then you can begin to judge similarities between stories on the basis of the concepts they contain, not just the words that they contain. So one story might be similar to another because they both involve revenge, even though neither story contains the word revenge. So what we're doing then is we're measuring similarity on the basis of these higher level concepts. Sounds like intermediate features to me. In fact, that's where we got the idea, by reading Shimo's paper on intermediate feature visual recognition. We wanted stuff, we measure similarity not by the low level stuff because that's everywhere, and not by exact conformity to a particular plot line because that's nowhere. Instead, we look for the intermediate things like regression, revenge, and so on. And so up here, what we have is we have 15 conflict situations described and read by Genesis and compared on the basis of the concepts they contain, whereas down here they're compared on the basis of the words they contain. So the lighter it is, the whiter it is, the more similar things are judged to be. So that means the diagonal is, of course, completely white because stories are more similar to themselves than they are to anything else. And the important thing is that they're different. So over here, you can see that there's a similarity judgment between the Persian Gulf War and the Afghanistan Civil War. It's pretty bright up there at the concept level, but pretty dark down here on the word level. So stories are similar according to the concepts they contain, not according to the players involved, when you look at it from a kind of intermediate teacher point of view. Gap filling is something we do in preparation for doing an analogical reasoning. Here is a rendering that I was told about by a political scientist. So I'm not vouching for the validity of any of this. I'm only telling you what a political scientist told me. So he was drawing he was talking about why we need intelligent systems to help us in doing political analysis. And this is the example. It's description of the Tet Offensive in Vietnam. So you can read through there. You see that, we could see that they were mobilizing. No, we didn't think they would attack because they knew they would lose and so on. So now we fast forward a few years to the Arab-Israeli conflict. What happened? Of course, they promptly attacked. And so according to one school of political thinking, they attacked in both cases for political rather than military motive. But the point is these things do run parallel. And so how can you make a judgment about why these things are running parallel? How do you put them into alignment? We've actually borrowed technology from molecular biology to do this. Because who are the custodians of knowledge about how to align sequences? It's the molecular biologists who align protein sequences and DNA sequences. So we adapted that technology to align story sequences, and we put the Tet Offensive and the Arab-Israeli War in correspondence. That enabled us to fill in the gaps in one with the other, and that's how we were able to do that kind of alignment. That's showing how even in the fog of war, the system might be able to spot things. Not that will happen, but at least it might draw your attention to things you should be thinking of. We like to think of this sort of system in the future as a kind of blunder stopper that tells you what kinds of things you're concerned about. Because no system's going to have a crystal ball and tell you exactly what's going to happen. So one system might know stuff that another system doesn't know. So you can think about one system teaching another system the things that it knows. So in this next demonstration, and we're coming close to the end. In this next demonstration, one system is telling a stupider system, a less intelligent system, things that it thinks it doesn't know. So there's a little zoom in on what you saw in miniature. So the teacher has a model of the student, which suggests that the student is from Mars and doesn't know anything. So at this particular point in telling the story, it has the option of spoon feeding and just saying, oh, Duncan becomes dead, or it can give a little bit of an explanation by saying he becomes dead because of his murder. But of course, the receiving system has no idea whether this is just special for Macbeth and Duncan. Maybe other kinds of people don't get dead when you murder them. So it has the option of going into a more elaborate explanation and giving the principle behind the conclusion. So this is a system operating in teaching mode. Now, my colleagues have seen this sort of stuff till they're almost ready to turn blue in the face, so I thought I'd better include something here that I couldn't have shown you 10 days ago and which they've never seen. But this, I'm going to hazard a live demo. My computer, of course, is connected to the web, which means it's connected to Boris's parser back up at MIT, which means that we can actually run it. And so what I'm going to do now is I'm going to run a version of, I don't know, well, we might as well use I'm flipping a coin in my mind. It's going to be either Hansel and Gretel or Macbeth. I'll use Hansel and Gretel, I guess, because it's a little different. And the question is, what do you think about I don't know if you remember the story, but this guy leaves his children in the woods. His wife persuades him to get rid of them or something like that. He feels bad about it in the end. So the question I'm addressing is, how do you tell a story to make it look good? How do you tell a story to make it look bad? And the answer is, you make a person look good or bad by adjusting the details that you suppress and the details that you emphasize and put in boldface, so as to draw out the kinds of conclusions you want. So this is a subject of a master's thesis that we just submitted this semester. So go up here, start the demonstration of persuasion, Hansel and Gretel. And we cross our fingers and hope that it works. It's reading away, it's absorbed some common sense rules and some concept patterns. Now it begins to create the elaboration graph, finds various concepts in it. Now it's done, but now it starts working again because we've asked it to retell the story using Morris's generator in a particular way that makes the woodcutter be likable person. So we'll just go in here and see what kinds of stuff is concluded. Oh, by the way, in making somebody look likable, what else? The other thing you do is make everybody else look unlikable. So you'll find a mixture of those kinds of things in the story as we have here. Yeah, there's the witch trapping Hansel in a cage. That's because we're trying to make her look bad, because we're trying to make the woodcutter look good. Anything that makes the witch look good, like building a candy college, we suppress, cross out, don't want her to help anybody. The woodcutter tells the truth to Hansel and Gretel about the plans. He's being honest now, so that makes him look good. The wife locks Hansel and Gretel in a room. It makes her look bad. The woodcutter doesn't help. We're trying to get all that suppressed because we're trying to make him look likable. The woodcutter becomes relieved. Yep, that makes him look likable, so we highlight that. So now we're beginning to be able to tell a story with a certain sensitivity to how what kind of impact we want to have on the reader in terms of their opinions about various kinds of things that happen. So that's a live demonstration too. I'm glad I passed that part. Let me get back to my slideshow because next thing to talk about is a couple other hypotheses. See, I've got two hypotheses so far. One is the interlanguage hypothesis. That's the thing that makes us different. In fact, we have this symbolic capability that allows us to build descriptions, and that's our interlanguage. And we have the story hypothesis. So that's the differentiating characteristic of us humans. And now I have social animal hypothesis, which is that it's a good thing that we can talk to each other. Or we do talk to each other, and that amplifies everything else. See, the outer language, we wouldn't need an outer language unless there was somebody to talk to. And we wouldn't have any outer language at all if we didn't have anything to say. A point that's often lost on politicians, but nevertheless it's true in most circumstances. So I think we make ourselves smarter when we talk to other people. But we even make ourselves smarter when we talk to ourselves. I always like to talk about this experiment that was done by a friend of mine, Michelin Shi, some years ago. She was teaching people how to do physics problems, elementary physics problems. You remember all this sort of thing, force balancing and all that sort of stuff. And what she did is she trained them up to be able to handle these kinds of problems in an elementary way. And then she gave her students a quiz. And what she found is that the top half did twice as well as the bottom half. And then she looked to see what kind of characteristics the top half had relative to the bottom half. And by the way, she was asking them to talk out loud as they solve these problems. So now you know what the result's going to be, right? So the worst students said about 10 things to themselves out loud when they were trying to solve problems. And the good students, the one that did twice as well, said 35 things to themselves. Some of this stuff was about problem solving. I'm stuck. I think I'm making progress. Other things were physics facts. I better see if I can consider gravity, things like that. But the interesting thing is that the ones who did well talked to themselves a lot when they were solving the problems. Of course, this is only in one direction, but we can't make too much of this because what we don't know is if you tell a lot of them have to talk to themselves more, if it actually helps. But the point is that talking to themselves seems to make them smart. So that it's as if language provides access into knowledge. It actuates indexes, brings stuff in. Now I bring myself back to the vision world because, of course, all of this is just manipulating symbols inside of a computer that doesn't understand anything on the outside world, unless ultimately it's connected to perceptual systems. So being connected to perceptual systems is very much part of the CPMM agenda, and everyone's given examples going in the other direction, so I would like to do mine. Because I think that our language system, our story system, has to make use of our perceptual system to do what it does. So I can say to you, John kissed Mary. Did John touch Mary? Yeah. And you can. How do you know? Did somebody tell you that? Did somebody offer it up in one of these cloud deals, which is trying to record all human knowledge? Or did you just imagine the kiss and read the answer off of the imagined scene with the perceptual apparatus? Eventually it becomes part of your lexicon. It's a rule. But originally, I think you imagine it and you see it. So there's your imagination blurred out to be an imagination. But that's what happens, I think. But now let me give you a couple other examples that involve Shimoda's routines. So here's example number one. How many countries in Africa does the equator cross? Anybody know? Anybody sure enough to bet their life on the answer? Probably not. But now you can know, and you can run that little visual routine across that line and count up the countries. And what are you doing when you do that? Well, you're performing, your visual system is following a recipe. But following a recipe is like, well, a recipe is a sequence of actions. So it's a kind of special case of a story. So all these things are kind of knitted together. Here's a more grisly example. I like to make stuff. I have an engineering gene. So I was installing a saw a while back with a cabinet maker. And a friend of mine said, by the way, you must never wear gloves when you operate this machine. Never wear gloves. You know why? Probably everybody, some of you who do woodworking have been told to do machine shop stuff. But others may not know why you don't want to wear gloves, but let me help you along. You know, the kind of gloves I'm talking about is kind of loose cotton gloves. And the question is, what kind of disaster could follow from wearing a loose cotton glove around a spinning saw blade? Now you've got it, right? You can almost feel your hand being drawn into the blade and getting mutilated. So that's another example of something you know because you can generate that knowledge on the fly using your imagination system. So every once in a while, someone gets out the back of an envelope, calculates how many facts you can know, and you can do that too. Just you just say, well, let's see, I can get a fact every 3 seconds. That means I can get 1,000 an hour. You can multiply that times 10 hours a day because you need some rest, and you multiply that times 365, you know the number of facts you can get in a year, and you multiply that times 20, so you know what an adult knows. But that's only actually a fraction of what you can potentially know. What you potentially know is more derived from stuff like this, stuff you can imagine and conclude from what you already know, on the fly, as needed. Oh, and now, one more example of the intersection of story understanding and vision. You all know about Schrodinger's cat if you're a physicist, but if you're in our world, you have to know about Ullman's cat. This is you actually saw this in one of Shimon's slides, and I borrowed it from him, and tell the story very frequently because the question is, what's the one-word answer for what the cat is doing? Not a trick question. It's drinking, right? So what's the one-word answer for what I'm doing? I'm also drinking. And now if I put myself in this posture and salute you for this wonderful summer school that you're attending and your attention that you're paying to my talk, what am I doing? I'm toasting. Which two look more alike? Well, the two that look more alike are different labeled because they tell a different story. And one is a story about thirst, and liquid, satisfying thirst, and the other is about something very different. So ultimately, I don't know. That's why I asked some other questions about visual routines and whatnot. I don't know how much an animal without storytelling, recipe following capability can know about what's going on in the world. To take a brief aside, my thinking about this, however, is a little bit tutored by the work of Matt Wilson recently, because his work shows that even those rats have a pretty good sense of sequences that move through a maze. It astonishes me. It's been known through his work for many years that they dream that path as they go through the maze when they're sleeping. But what I learned from that quite recently is when they get to the goal and find some food, then they play the sequence in their brain backwards, as if they're trying to remember how they got there the next time around. End of aside. So this is where I think the Genesis system contributes in this enterprise. We have some hypotheses that are story-focused in terms of understanding what we humans, what goes on inside of our skulls. We're attempting to follow sound methodological steps. We, being engineers, believe you can't really understand it unless you can build it, so we're building a system, and that system demonstrates all of these kinds of story understanding capability. And I chose that word extremely carefully. Illustrates, not demonstrates. We should all follow Andre's example and talk about what our systems can't do. And what our system can do is it can illustrate a lot of these sorts of things. But what we can't do is we can't scale it up to deal with the real story. We can't scale it up to deal with real Macbeth. We can't scale it up to deal with dialogue. We can't scale it up to deal with Dickens. We looked at Dickens. We looked at David Copperfield. And if you look at some literature like that, what you discover is that, first of all, there are no causal relations anywhere to speak of, because he assumes you already have all your common sense. Next thing you find is sentences of more than 100 words are frequent. You have more than 100 words. Very complex stuff with embedded clauses all over. So it'll be a while before we can build real blunder stoppers for real people and have practical applications. But meanwhile, we think we're shedding some light on the nature of human intelligence by looking at what it takes to understand the story. And that is the end of the story. Questions? Yes.
I guess two parts to the question. First of all, there's a big leap between the symbolic representation of, as you showed, the blue wall, and then you leap straight to language. So what happens between this gap, and do we need language to reason about vision, for example?
Yeah.
And the second question is, because you showed an example of a different language, and that's an electrical circuit.
Yeah.
So could you implement some sort of reasoning as did here, but on circuits or maps or things like that?
Yeah. Well, two interesting questions. First of all, I will answer your first question, which has to do with that blue wall business, and do we need language to do that? What we need is a capability that seems to be closely connected with language, namely the ability to take information from two very different modalities, namely geometry and color, and put them together. So it's interestingly related to Chomsky's remarks about putting concepts together. That's what we seem to do when we solve that problem, put two concepts together. And it doesn't seem to be the case that rats and small children can do that. Oh, I forgot to tell you, but when did small children become adults? And the answer is at about 5 or 6 years of age. But what it actually correlates with is the onset of the child's use of the words left and right in their own descriptions of the world. So that's what seems to break through that barrier. So it's to summarize that answer, it's the combination capability, the merge quality that seems to be intimately connected with language that makes that possible. So it's not exactly clear we need one to do the other and the other to do the one. They're all tightly connected together. And the other question was...
limited this on other languages such as math,
such as how do we view these other things as story understanding, like doing math and so on? Well, we have gut feelings about that. We don't have any demonstrations or illustrations. We know that our story understanding capability can be used to deal with all the kinds of things you always learn by case study. Medicine, business, law, we've done illustrations in all those kinds of domains. We believe that the others are a matter of recipes being a special case of story understanding. And then for each domain, you have a different kind of recipe. So we have thoughts about where to go with that, but we haven't proved anything yet. Yes?
Do you think there's a limit to the number of concepts we can have? And do you think we've reached that limit? You could answer either of those.
Do I think there's a limit to the number of concepts we can have? No, because we can make new ones when we need them, or on the fly, as appropriate. We have a song at MIT, it's a drinking song. And I always tell my students there are an infinite number of verses. And what could that possibly mean? Well, it means that if there were a finite number, then someone would make up another one, and so therefore it's effectively infinite. So I'll use the same argument here. Our potential for having another concept is unbounded. At any given time, have some finite number. And you can work out those numbers on the back of the number, too. You can say, well, each concept needs a story that goes with it. How many stories can you accumulate in 20 years and just work out the numbers? It's not big.
You don't, well, I mean, we can have more stories now than we could have had, 10,000 years ago, right? Because there's more concepts in our environment that we're given, right?
I guess I would say that there are probably concepts that they had that we don't. For example, I know how to use a table saw, but I baffle me if they put me in front of a stone and told me to make an axe. When I was an undergraduate, we learned how to do multiplication with logarithms, but you don't do that anymore. So concepts come and go. We have finite brains, so I would say that at any given time we have a finite number of concepts. But we can generate new ones by blending old ones in interesting ways and by being creative about how we blend them. So we can get new ones by new stories being told to us or by our own creative generation of new stories. Any others? Okay. Yes.
So there are some properties of stories and properties of concepts that have sort of similar names, and I'm wondering if you think that they're the same thing, like coherence or redundancy in inscription or something like that. Is it possible because what makes a good story is what makes a good concept?
The question is, what about some other ways of looking at stories like coherence? And yes, we're starting to look at questions like that. We've done some work with some students of Rebecca Sachs having to do with story coherence. And is a story interesting? Is a story surprising? Is a story memorable? Those are all things we think we can put more substance into by virtue of the fact that we have machinery for modeling those kinds of things in a way that builds on top of what we've got. So coherence might be how long is the chain in the story? How much does it break up into little clusters of independently connected stuff?
Yeah, there's a similar notion in concepts, like some concepts are hard to learn than others, and that's supposed to be because they're less coherent or something like that. And so I'm wondering if that is supposed to be like the same.
Well, that's right. I completely understand the question, so probably better deal with that offline. One of the things, of course, we're interested in that has at least a keyword in common with what you said is we're interested in how we might have a system discover concepts on its own. Where sometimes people complain that we're spoon-feeding everything that the system knows to it because we're providing the rules and we're providing the concepts. But on the other hand, I think that mostly what we know is told to us too, so I'm not embarrassed by that. Nevertheless, we are interested in and have begun to build systems that will take an ensemble of stories and look for common patterns in them, which will then become candidates for being concept patterns. They wouldn't have names like revenge, but they would be there as the equivalent of the concepts that have been told about. One more, yes.
Two-part question, depending on the...
Two more. Okay.
Is there a difference between storytelling and explanation?
Is there a difference between storytelling and explanation? Sure.
Okay.
I mean, I don't have a story to tell because I haven't thought about the question enough. But, I can tell you a story, and I may or may not provide the details that would accommodate to my model of how well you understand what I'm telling you. So an explanation would build into it my understanding of what you understand so that I can be educational as well as merely relating events.
So is storytelling a superset of explanation?
Let's see, I'm not sure which way the containment goes. I would say that a longer story would be one that provides not only the sequence of events, but a greater amount of explanation for how the pieces fit together. So if containment is smaller, then I would say explanation is contained storytelling.
And do you have any ideas why 4-year-olds ask so many why questions?
Do I have any idea why 4-year-olds ask so many why questions? No, but I think we could model it. Because when you tell a story, some of the elements of the story are at the left side, and they don't have explanations. So those would be the questions that you would ask, why? So in the Macbeth example, Lady Macbeth persuades Macbeth to want to be king. And there's no explanation for the story as we've told. So it would be natural to ask why and get an answer, well, she's king or something. So by asking questions about the stuff on the left side, stuff that connects into the story but doesn't itself have explanation, you can imagine the system building up